So today we're going to talk about the different ways that planes can intersect in 3D space. Our planes, so when we say planes, we're going to take a look at a scenario where we have two planes or a couple scenarios. And then we'll take a look at some scenarios where we have three planes intersecting in 3D space. Let's start with two planes. So if you guys imagine two planes, I could have two flat planes that are parallel. So they can be parallel and distinct, meaning they will never intersect one another, so 0 points of intersection or 0 areas of intersection. I can have two planes that are parallel and coincident, which gives us infinite points of intersection. Or if we just imagine that we have, like, if you just take two papers or whatever, and they're any other orientation, how do they intersect? They intersect in a line. So those are going to be kind of what we're checking for. So let me just get this up here. So we're going to take a look at this set of planes first, and I would say we always want to check first to see if the planes are parallel. If they're parallel, that's going to save us a lot of work. So the easiest way that we can check the equations of planes and how they intersect is if they're in scalar format, or sometimes called Cartesian format, because we can actually see the normals here. So here is 1, and we see if the normals are scalar multiples of one another. So are the normals some scalar multiples of one another? So our normal number 1 is 1, 4, 2. Normal number 2 is 2, 8, 4. Are these scalar multiples?
Yes.
Okay. What's the scalar multiple?
2.
Okay, so 2 times normal 1 is equal to normal 2. Okay? If the normals are parallel, we know that that must mean the planes are parallel. Okay? So parallel normals means parallel planes. So therefore, the planes are parallel. And then we just need to decide if they are parallel and distinct or parallel and coincident. Super easy to do when we have an equation in scalar format. The constant part of our scalar equations, the 10 and the 6, if that follows along with the same scalar multiple as the normals do, they are parallel and coincident. If it doesn't follow along with the same scalar multiple of the normals, they are parallel and distinct. So here's the question. Is 2 times 10 equal to the scalar multiple from the second plane, 6? Or not scalar multiple, but equal to the constant. Okay, so this is not following along with the same scalar multiple, right? So because those are not equal, they are parallel and distinct. Okay, so we would say 0 points of intersection. Okay, so we'll check, essentially what we're doing here is we're just checking to see if the constants of the planes have the same scalar multiple as the normals. It's hot in here. Does that make sense? Super quick check that you can do when you're in Cartesian format or scalar format. Questions? Okay. So we'll take a look at a second scenario here. We're going to describe how these planes intersect. If they intersect, we'll find that particular line of intersection. So the first thing that we're going to check is the normals. So we're going to check if normal 1 is some scalar multiple of normal 2. So if we take a look here, normal 1, if we call this maybe plane 1 and plane 2, normal 1 is 2, negative 1, 1. And we want to see if that's some scalar multiple of 1, 1, 1. I think we can just tell that by looking at it. Are they scalar multiples? Okay. So this is not equal, so therefore the planes must intersect in a line. They're not parallel. Okay, so that's our first little check that we're going to do. Okay, if that is not present, then I'm not going to check the scalar multiple of the constants of those things because I already know that the planes aren't parallel, so I have to do something different. So what we're going to do here is we're going to set up plane 1 and plane 2. Actually, I can just do it right from here. And we're going to use elimination. So our goal is to eliminate one variable, either x, y, or z. Doesn't matter which one. Choose the easiest one. I think here we already have like a positive and negative y, so maybe we can just add these equations together. So I'll get 3x, the y's will cancel, plus 2z minus 7 equals 0. Okay, so that's your second step. And then, because we have 2 equations and kind of 3 unknowns, there's no way that we're actually going to be able to solve for an x, y, and z. This should make sense because if I solve for an x, y, and z, I'm saying that these planes intersect at a particular point. So it won't be possible for me to solve for x, y, and z. So the route we take here is we will pick a remaining parameter, or not a parameter, but pick a remaining variable. Either, in our case, it will be either x or z. And we're going to set it equal to our parameter. So we know for a line, for these 2 things to intersect in a line, we need to have some parameter t. So this equation, when we used our elimination here, is going to help us find how we can set those up with that parameter t. Okay, so for example, in our case, maybe we'll let z equal t. Or I should say z, because we're Canadian. Okay, so our job in our equation here is to solve for the remaining 2 parameters, so the one that we did not let equal, sorry, I keep saying parameter, variables, the one that we did not let equal t in terms of our t parameter. So I want to solve for x, and I want to solve for the y. That makes this all kind of work together. So I'm going to use our equation from our elimination first. So I'm putting t in for z. And what this allows me to do is it allows me to kind of find, oh sorry, that was equal to 0. It allows me to kind of figure out the parametric equations for my coordinates here. So z is equal to t. That gives me the z components of my point, my position vector, and also my direction vector. So the point z component is 0, and the direction vector z component is 1, because it's 1t right here. And then I find the extra components in terms of x's and y's. So I'm going to isolate for t here, or I'm going to isolate for x so that I can have the parametric equation, sorry. So bringing over 7 and the t and dividing out 3. Okay. It would be helpful if we could know the individual components of these, which are 7 over 3 minus 2 over 3t, just so that we know that this one's going to be for our position vector, and this one will be for our direction vector. And then in one of my other equations, I will actually sub this in. So I'm trying to get y completely in terms of t. So I'm going to actually sub this in for x in one of my two original equations. I think that the second equation here will actually be easier because there's no coefficient in front of the x. So in my equation, x plus y plus z minus 6, we're going to get y completely in terms of t. So I'm subbing this in for x in here. Y is y. We'll isolate for that in a second. Z, we said we would let that be the parameter t. And then I'm just going to isolate. We'll combine the t's. We'll combine all of these things, and then we'll simplify here. Yeah. So I'm going to just make this 3 over 3t and negative 18 over 3, just so we can add the coefficients of those t's and add the constants together. So I think we're getting 1/3 t. And we're getting negative 11 over 3. And then we're just going to move everything to the other side here. So it'll be 11 over 3 minus 1 over 3t. Okay, we actually just found our 3 parametric equations. From our 3 parametric equations now, we have one in terms of x. We have another in terms of y. And we have one in terms of z. It's just z equals t. So can someone find our vector equation of our line of intersection for us? We'll call it r. What's the position vector? Great. 7 over 3, 11 over 3, and 0. And the direction vector? Awesome. Okay, I can let this vector equation, if I just want to simplify this direction vector out a little bit here. Sorry, that's not a plus, that's a comma. I can let this direction vector here, just by multiplying everything by 3, just be negative 2, negative 1, and 3, just to kind of simplify that a little bit. Okay, because we know it can be any scalar multiple of the direction vector. How could I check my answer? What are we plugging into the main equation? Plug t in where? But there's no t in here. Could I check that this point is on both of the planes? How would I check that?
You plug it there.
Yeah, so if I plug it in here and I plug it in here, that's not like a full check, but it's definitely something that I can check just to double check that my point is correct. I can also generate a variety of other points on here and I can check them in my planes just to double check. That would be a good way that we can double check that. Okay, so this is a position vector. It's also a point on which should be on both of the planes. So if I generate maybe like 3 points and I check them in both of my planes, it should give me a true statement in there if I check. So you can check your answer. By subbing in points from your line above into both planes to double check that they're on the plane. Okay, so you're going to generate maybe like 3 different points. I think that's probably a good check. And then just sub them into both of your planes and make sure that they're on the plane. If it doesn't give you something equal to 0 up here, if it doesn't let the left side be 0, that's a problem. Cool? Any questions? Okay. Let's continue. All right, so the second that we slide in an extra plane here, the possibilities get much larger. So intersections of 3 planes. I'm actually just gonna, do I have the textbook here? No, I don't. I'm gonna just pull it up quickly so you guys can see visuals of what's happening. Okay, so page 485 of your textbook has some pictures for you. So this is 2 space. So this is actually kind of what we were talking about, what we just discussed. So we actually just found a line of intersection for both of our 2 planes. We have parallel coincident, parallel distinct. Now we're going to check out what happens with 3 planes. So a system of 3 planes, we can call it consistent if it has solutions, essentially. So 1 or more solutions. We can have a bunch of different varieties of what happens with 3 planes. So if you imagine 3 papers and the different ways that you can kind of arrange all of those, I could have 3 planes, so 2 of them intersect at a line, and then 1 of them crosses through, and that would give us a point of intersection. I could have all 3 planes intersecting in 1 single line, okay? We can have coplanar. So these are what we would call consistent planes because they have solutions. So it can be an solution which is along a line, it can be a solution of a point, or it could even be infinite solutions. So we would call that consistent. Inconsistent, no solutions. So I could have 3 parallel planes. I could have 2 parallel and 1 kind of cutting through. So 2 of those have an intersection along a line, but the line of the intersection for the other one is different. So no definitive point where all of those 3 are crossing. And then we can also have this kind of like triangular thing that's created where they intersect at 3 different lines. So all of these would be considered inconsistent systems. Okay, so we're going to just kind of break it down on our note here. So we can have no intersection, and there's 2 ways that this can happen. 0 intersections. Okay, so we'll do 1 and 2 here. So we would have any 2 of the 3 planes being parallel and distinct. Okay, so this is the example that I showed you where you have like 1 plane here and 1 plane here, and then the other plane kind of like crosses through them like this. So we get 2 different lines of intersection in that scenario. So we would need 1 single line of intersection for all of them for that set of planes to be considered consistent. Okay? The 3rd one will not be parallel to the other 2. That's a different situation. Okay? The other thing that we can have is 3 non-parallel planes. With coplanar normals. Essentially what this means is it's kind of saying that we have, so like if I have normals that are all parallel to one another, or like 2 normals that are parallel to one another, I know that that's not going to produce 3 different normals that make a plane. So essentially this can kind of happen like, so if I have my 3 planes that form this kind of triangular piece, this shows it a little bit better in 3D. Okay, all of these normals, when the normals, oh, I guess I can actually write on this too, which is cool. All of my normals that are kind of like sticking out from each of these are forming their own plane, right? So they are coplanar normals, even though the planes have no solution of intersection. Okay, that means I can check for coplanar normals. What's the check that we do? I know if vectors are coplanar, a set of 3, if
Cross product,
triple scalar product is equal to 0. So the normal from the first crossed with the normal from the second, dotted with the third, would actually equal 0 if the normals are coplanar. Okay, so this is a check that we kind of start with for a lot of our stuff, just to kind of get an idea of what situation we're looking at. Infinite intersection. So this can happen also in 2 ways. Okay, this can happen in the form of 3 parallel and coincident planes. So all planes are parallel and coincident. Okay, which means that normal 1 is going to be some scalar multiple of normal 2 and some scalar multiple, let's call it m with normal 3, right? So the normals are all scalar multiples of one another, and also we would be checking their constants as well, to check that the full equation is also like scalar multiples of one another, okay? Just as like a little sample for you guys, we can see here that if I have this section of 3 planes, okay, these would be all scalar multiples of one another. Okay, so the first plane, if I multiply it by 2, I get the second one. If I multiply the first plane by 3, I get the third one. And then there's, I think this is what, 3/2 or something like that to get our third plane from number 2. So they're all kind of like different versions of scalar multiples of one another, okay? Including, I'm looking at the constants as well, right? To prove that they're parallel and coincident and not parallel and distinct. Okay, the other way that that this can happen is if all 3 planes intersect in a line. So I'll just show you that example here. So this is the scenario I just showed you. So we'll find all the normals are parallel along with the constants, they're scalar multiples. This is the other way that we can have infinite number of solutions, because there are infinite points on this line where our planes are intersecting. So all 3 planes intersect in a single line. Okay, and what this would mean is you also have coplanar normals in this scenario. Okay, so if I have my 3 planes, if this is like a side view of kind of what I see with my planes, they're kind of all intersecting like this, and then they intersect with like a line. So I would be checking the triple scalar product as well, just to double check and see if that is equal to 0 or not, and that will kind of narrow down a little bit. Okay, and then the last way that we can have a solution is we can solve a system of 3 equations with one point of intersection if we have 3 non-parallel planes. With normals that are not coplanar. Okay, in other words, my triple scalar product will not equal 0 in this case. Okay, this one's a little bit harder for me to kind of like draw, but you guys saw it in the textbook here. That is this scenario where we kind of have like 2 of them will intersect in a line, and then the other one kind of cuts straight through, and then we have that one single point of intersection there. Okay, so there can be a way that we can do a quick check just to start. So on this page, we're going to do our quick checks to decide whether we have a single point of intersection, no intersections, or infinite intersections. So we're just going to double check a couple things to start, and then where we need to, we'll kind of go and we'll check some of these a little bit further. Is everyone good with this so far? Any questions? Okay, can I scroll down from this? Gabriella, do you need a second here? You're good, or you need a second? Okay. All right, so your very first check for every single one of these ones is we're going to check whether they are parallel or not, okay? I'm going to put this kind of more over here so I have a bit more space, okay? So your first check always, we're going to check for parallel planes. All right, so we can kind of just do this by observation. If I were to make these x's multiples of one another, I'd have to multiply this whole equation by 2, right? So if I try to make these the same, then this will be 2x plus 2y plus 2z plus 4. So I automatically know these two are not parallel, okay? I'm going to check the second and the third and also the first and the third just in case I have 2 parallel planes and then the other one cuts through the both of them. So for instance, here if we tried to make the z's the same, I'd be multiplying this whole plane by -2. That leads me to get -4x minus 6y plus 2z equals 22. So again, not scalar multiples of one another. And then in order to make these the same, I'd have to, let's just say we focus in on the x's here, I'd have to multiply this whole equation by 5. So 5x plus 5y plus 5z plus 10, not the same equation, okay? So if there's some scalar multiple that I can multiply by one of the equations to make those equations the same, that means they can be parallel. If the constants happen not to be the same, they're parallel and distinct. If the constants with that multiple end up being the same, they're parallel and coincident. So here we have no planes that are parallel. Okay, so as soon as we don't have planes that are parallel, I can rule out a couple things. Either they intersect in a single point. I'm ruling out that all planes are parallel and coincident, and I'm also ruling out that there are no intersections because 2 of the 3 planes are parallel. Okay, so my options that are left are I could have 3 non-parallel planes with coplanar normals. I could have 3 planes that intersect along a line, or they could intersect at a point. So I can narrow that down one more time by checking the triple scalar product. So that will be our second step here. So we're going to check if the normals are coplanar. I guess I don't need a dash in this word. Just coplanar like this. Okay, so we're going to check the triple scalar product. So we're going to cross 2 of them. So 1, 1, 1, maybe we can cross that with 2, 3, negative 1, and then we'll dot it with 5, negative 2, 2. Okay, so I'm going to let you guys take a second and do that. We'll pause the video. When you use cross product here, you should have got the vector negative 4, 3, 1, and we're dotting it with 5, negative 2, 2. And then you'll see here when we do the dot product, we're getting negative 20 plus negative 6 plus 2, and that gives us negative 24. So because this is not equal to 0, we automatically know that the only solution that we have left here is, what is the option? Yes. So if the normals are not coplanar, and I don't have any parallel lines, the only option I have left is that all these planes intersect in a single point. Okay, we're going to use the next pages to actually find what that is. Okay, but I want to check the other ones first before we continue that. Okay, so these are the quick checks that we do just to kind of get us started here. Any questions on this so far? Okay, so first check here on our next one is we're going to check for parallel planes. Can you guys see any parallel planes here?
No.
Are you certain?
Yes.
Just making sure. Okay, there's none. None of these lines are scalar multiples of one another. You can usually just kind of see that visibly with your eyes. But if you need to check the ratios of all those things, you can check that too. Now we're going to check for coplanar normals. Keep putting a dash in this word. Okay, so we're going to do triple scalar product here. So we are going to do 1, negative 4, and negative 4 crossed with 3, 1, 1. And then we're going to dot it with 11, 5, 8. Neil, let's see if you can redeem yourself here. Pause this for a second. Yes, did you? So from crossing the first two vectors, we get 3, negative 13, 4. And then we're going to dot it with 11, 5, 8. And then you should get 33 plus negative 65 plus 32. And that actually gives us 0. So that tells us that the normals are coplanar. It doesn't narrow down for us, unfortunately, whether we have this scenario where they're all intersecting along a complete line, or whether we have 3 non-parallel planes that are kind of intersecting in 3 different lines. So I could have 0 points of intersection if I have the case where they're kind of like forming a triangle and intersecting all along a line, or I could have infinite, and I have to check a little bit further. We have to do some more calculations to decide on that, so whether they all kind of cross along the same line. Okay, so those are my options. We will have to decide further once we do some calculations on these. Okay, you guys are going to check the last one, so check for parallel planes first. And then you're going to check the normals. All right, so we can kind of visibly see here that there are no parallel planes. I kind of purposefully did this because these two examples are really easy to tell if all 3 planes are scalar multiples of one another. This is also pretty easy to tell too if there's two that are parallel and a third one that's not. So there's no real math that we have to do with these first two in these categories here. We're just kind of like observing the set of planes and then deciding from these two. Okay, an example of this one, just so you guys have an actual example in your notes, could be something like this, where you have, we're just looking for two parallel. And even if they're parallel and coincident or parallel and distinct, it shouldn't matter. Or actually, I guess it does matter, because if they're parallel and coincident, then you have a single line of intersection. So they need to be parallel and distinct. So let's just say we had something like this. We can see that two of these guys are parallel. These are the two that we kind of observed earlier that were parallel and distinct. And then this third one is not parallel to either two of those things. So I'm really just looking at this by observation. I can see the normals are scalar multiples of one another. The constant doesn't follow along with that scalar multiple, so they're parallel and distinct, and the third one is not. So automatically I know I have no point of intersection for that one. No math really needed other than multiplication. Okay? So with this one down here, when we're checking for coplanar normals here, I got the cross product of these two normals as 16, negative 8, negative 4, and then I was dotting it with the last one to get 16 minus 16 plus 0 here, or I guess it's plus negative 16, so we get 0. So again, I have these two final options here. So either there's 0 points of intersection, and these are intersecting in this like triangular kind of pattern along 3 different lines, or infinite along a line of intersection. Okay, so they're all intersecting at one particular line. Okay, do we need a break before we get into hashing the rest of this out? Anil says no, he's ready to go. All right. Is everyone good on copying? You good? Okay, Jason, are you good? Okay, so let's start with the first set of lines. A single point. So single point example with our first set of lines. Just to remind you, these are our lines that we're working with. It was negative 11. And okay, so we're gonna, as we always do when we're trying to solve a set, this one I have 3 equations and 3 unknowns, and I know they intersect in a single point. This should be, when I have 3 equations and 3 unknowns, this should be solvable with elimination / substitution if you really want to do substitution and you're strange like that. So let's just call this equations 1, 2, and 3. I'm going to take equation 1 and just multiply it by 2 so that I can eliminate maybe the, or actually, you know what? The z's are already the same. What were you going to say, Aiden?
Yeah, I just going to say.
We'll just add them. Yeah, perfect. So we'll take equations 1 and 2, and we're going to use elimination. I played this again, right? Okay, just double checking. Okay, so let's stack these guys. So we're going to cancel the z's because they're super easy to cancel. And one's positive and one's negative, so we'll add these two. So we'll get 3x plus 4y equals negative 9. Okay, and then we're going to kind of do like our little parameter thing. So we're going to let either the x or the y, one of the remaining parameters, be t. So for instance, let's say we let x be t. Okay, one or the other, that's remaining. And we're going to solve for y in terms of x being t. So if I use this equation here, and I sub in t for x. And then I want to just isolate for y here. Okay, similar to what we did with our two planes on the first page. And then I'll divide out the 4. So it'll be 9 over 4 minus 3 over 4 t. Okay, I'm also going to solve for a z in equations 1 or 2 with my parameter as well. So I found my y in terms of t. I also want to find z in terms of t. So I think it would be pretty easy just to use equation number 1. And if x is t,
it should be equals -9 for when you sub in x equals t. Because that's
oh yeah, sorry. Thank you. Appreciate that. That can cause everything to go awry very easily, so don't do what I just did. So let's use equation number 1 just because it's easy. And I'm going to solve, we have y, so I'm actually just going to plug this in for y. And I'm going to solve for z in terms of t. Okay, so I'm just plugging in my y and my z from my first, or my y and my x from my first equation, so I can solve for z there. Okay, so we want everything in terms of t. That will give us kind of like our parametric equations for that first intersection. So what I'm actually doing here in using these, solving for elimination with these two lines, is I'm finding the line of intersection from our first two equations. Okay? Let's just find a common denominator here. And we're going to gather our stuff together and isolate for z. So I'm just going to move everything over to the other side and kind of gather these things up as we do that. So here I'm getting 1/4 t, and when I move it to the other side, it will be -1/4 t. And then 9 over 4, when I move this over, it will become plus 9 over 4, and I will get 17 over 4 for t. Okay, I'm just going to box these up so we can see our parametric equations for our line of intersection for the first two planes. Okay, so essentially what we're doing in all of this part here is we're finding the line of intersection between two planes, two of the three planes. That's kind of what we're doing. Okay. So what I want to do with this kind of like remaining plane here is, now that I have the three parametric equations, we could express it as a vector equation if we want, but I don't think we really need to do that. I'm actually just going to plug them into my third plane and then see how these things kind of come together, right? So now I want to know this line that I have over here. I'll just box it in red for you guys. This line, I want to see how this interacts with this last plane that we haven't used yet. Okay, so we're going to plug the line of intersection. Into the last plane. All right, so we're interested in kind of what happens here. We know that this is going to intersect in a point, but supposing we didn't know, we would kind of be seeing what was going on here. So this is my last plane. And I'm going to go ahead and we let x equal t, so I'm going to plug in t for x here. I'm going to plug in the 2 times our y line. Maybe we can even, just because this already has a common denominator, maybe we can even just merge that kind of together and let that be all over 4, rather than like expressing these as 2 separate ones here. Okay, and then I'm going to plug in our last one. And again, I'm probably just going to merge these two guys together, just because I know I'm going to be able to cancel it with this value up here. So it'll be negative t plus 17 all over 4 equals negative 5. So I think we can actually, well, I mean, we could actually just kind of go through here and multiply everything by 4. I mean, we also can reduce, so maybe we'll reduce first. Let's do that. So 1 and 2, and 1 and 2.
T equals negative 3.
You're right. Too fast. Okay. If you have fractions, we don't like to isolate for things with fractions, so we can just come through and multiply everything by 2, every single thing, so that these guys can cancel. Okay, so this cancels, and then we can actually just kind of like drop the brackets here. So we'll have 10t plus 9 plus 3t minus t plus 17 equals negative 10. And then your job is to gather all the t's and solve. So I think we get here 12t plus 26 equals negative 10. And then when we isolate, t ends up giving us negative 3. Did we find the point of intersection yet?
No.
We have not. This continues. We're almost there, though, because we have 3 parametric equations that are already isolated for t. So if x equals t, then x equals negative 3. Okay, so this is the last step. We're going to find the POI. So x equals negative 3. That one's done. Y is equal to negative 9 minus negative 3 all over 4. So y is equal to 0. Hi, Lauren. I forgot you guys had a prefect thing today.
Thank you.
Okay, and then this gives us 20 over 4, which gives us 5 for z. Therefore, our final point of intersection.
Negative 3, 0, 5.
Great. Isn't this fun, guys?
Yes.
It's a long process. This was the first question, yeah.
The last part is pretty much the same as what we did before for a line.
Yeah.
It's just the first part.
Yeah. So this, if you notice, guys, this is actually what we did yesterday. This second part, we found the intersection of a line and a plane. So this is the same thing.
If you didn't get, if you didn't get that statement equal, to be true, then is it just that one line of intersection that you already found? Is that the option?
So in the case where you have, I mean, we would already know because the normals would be coplanar, right? So this is the only scenario where we would kind of see something like this happen with that point of intersection. Okay? I want to show you guys the other ones as well. I know today is a little bit long, but at least then you can kind of work on it over the weekend, and then you can start your reviews and be ready with everything that you need here. Any questions on this one before we move to another one? Okay. Okay, let's do the second set from part B. These are our lines. I'm going to label them 1, 2, 3. We know that either these intersect 0 times or they intersect infinite times. Mark and Anil, or just Mark, I guess now. You ready? Don't fall behind. Got lots to finish. Okay, so we found for this one that we could either have 0 points of intersection or infinite. So we're deciding whether these kind of intersect. So just to remind you, we're deciding whether they intersect in 3 different lines or one single line. Okay? So we're gonna start this off the same way. We're gonna choose 2 equations to start with, and we're gonna find the line of intersection of 2 of those things. So I know for sure that either these intersect in 3 different lines or they intersect in one single line altogether. So that's just kind of what we're gonna check. So the very first thing that we wanna do is we'll choose 2 equations to use elimination with. Because we want to find their line of intersection. Just line. Okay, I think probably the easiest one to eliminate is the y's out of equation 1 and 2. So I'm going to choose 1 and 2. And we can just add them together because the y's are already opposites of one another. So if you don't eliminate a variable here, you're probably doing it wrong, okay? You need to at least eliminate one variable. So when we're adding, we get 4x, and now negative 3z, and positive 3.
Does it matter what variable you set equal to t?
No.
As long as it's still in the eliminated equation?
Right.
So you could pick x or z?
Right. Okay, so I'm going to pick x for this one. If you want to test it by picking z, Aiden, you can go ahead. So let one of your remaining variables, either x or z, in our case here, equal the parameter. So I'm going to let x equal t, or you can choose z. Okay, I hate marking these tests so much because there's so many different answers and like things that people can do, so then I have to like comb through all of it. So, yes, don't like. And we are going to sub that into our new equation. Maybe we can call this equation 4. So sub x equals t into equation 4 so that we have z in terms of t to start. And then I'm just going to isolate for z here. So maybe we'll do 4t minus 3 equals 3z, and then just divide out that 3 there. Okay, so this is our first part of the parametric equations, our second part, and then we're going to sub x equals t and z equals this. Yeah. Don't know what just happened there. Into a last equation, choose the easiest one. I don't know which one is easiest here. You say 2? Yeah, true. Yeah, I think equation 2 is easiest as well. Okay, so we'll sub that into equation 2. So it'll be 3t. Yeah, you're right, because y is by itself also. Plus this in terms of t. So right now we're finding the line of intersection between the first 2 equations. That's what we're working with. So I would not, at this point right here, I would not sub these parametric equations into an equation that I didn't use in this elimination. So I'm actually not using this final equation here yet, okay? So don't use this one. We want to just focus in on the first set of equations first, and then we'll worry about the third one after, okay? So don't sub that back into one of those other ones. Okay, let's simplify here. So I guess we can just put this over 3 to create a common denominator. And then your y here is going to equal 1. And then this is 13, so it'll be minus 13t over 3. Or -1, right? Because when I bring it over, it will be positive. So there's our 3 parametrics for our first. We are going to, so this is the same process as what we did before. We're now going to sub our 3 parametric equations into the last equation that we didn't use in step number 1 for the elimination.
So Michaelis, for y I got -4.25 minus 2.25t.
What's that?
I got y equals -4.25 minus 3.25t.
Did you get the same thing for, but your z and your x are opposites, right? Kind of?
Yes.
So you'll probably find once you plug it in at the end that it all
Okay.
works out the same way. But yeah, you're going to get different parametric equations slightly because you put z in terms of t. So that's okay to get a different one. Okay, so in my third equation here, just to remind you, our third equation was this. In that set of 3, we're plugging in these 3 parametric equations just like we did in our last question, and we're going to check what comes of doing that, okay? So again, if you don't know like what to expect here, that's totally fine because we're just going to see what happens and we're going to see if it makes sense or doesn't make sense and then kind of go from there. I guess I can separate this out as well. Maybe we'll do -1 here. Was that a -3? Oh no, that was +3. Okay. All right, so actually, I guess the easier thing here to do is just to leave them and then multiply through everything. Maybe I'll just do that. And then I'll just multiply through with all of these 3 so that I don't have to worry about these fractions. Sorry, this isn't working for me now. Okay, so I'm going to come through and just multiply everything by 3 here. Hopefully I didn't mess anything up by switching that last minute. These are now gone, and these are gone. So we just have -15 minus, what is that? 65? Okay, and then just kind of simplifying from there. So I already see with my t's, I feel like this is supposed to be, oh no, it's not. I feel like those are supposed to cancel.
I got 14 equals 0t.
Yeah, so why is my thing negative here? What did I miss? I feel like that's supposed to be positive. Oh yeah, it is positive. Why did I put it as negative? So this is positive, sorry. So I'm already seeing here that my t's are canceling. So I've got 0t. You don't need to put 0t. You can just leave it as nothing, like it's gone now. And now I'm getting -39 equals 3. Does this make sense? No. So what does this tell me about whether this final line of intersection intersects or not with the third plane? Is this line on the third plane? No. Okay, so therefore we have 0 intersections. Okay, so we have this scenario where they intersect at 3 different lines. All the planes intersect at 3 different lines.
Do you have to solve for each line?
No, I'm not going to make you do that. Okay, so pretty much the same process every time. I want you guys to try out the last one, see what you can do with that, and then I'll kind of start posting up a couple steps to my solution as you're working, okay? Okay, so we're working with this set, and we're going to decide whether they intersect with 0 or infinite points of intersection using the same kind of process. So try that out, get a little head start, and then we'll take it up. Okay, so if you're just kind of trying this on your own here, the first little thing that you're going to do is choose a set of two planes from above and find their parametric equations for their line of intersection. So we'll start with elimination. I think the y's are really easy to eliminate here by just adding these two equations. And then you can choose a parameter. It can be whatever is remaining. So if we're eliminating the y's, you can choose the x or the z. And then find those parametric equations and check them in the last. Okay? So pause the video if you're still watching and see if you can kind of complete the rest yourself. All right, guys, so I used elimination up here if you want to just check this out here. I used equations 1 and 2. I got a fourth equation, and I ended up setting z equal to t just to kind of show you we can do anything. We can choose either of them. You can also set x equal to t and see what you get here. So I ended up subbing in z equals t into this equation, and then we're just isolating for x. So I have these two parametric equations. What did you guys use for your finding the y parametric equation?
The second one.
The second one?
Yeah.
Why second one?
No, I used the first one.
Yeah, wouldn't the first be easier?
Yeah, but
You just
gotta
wanted
do
to
yes.
shake it up a little bit?
But this one's actually, I don't know, it may be simpler. I got y equals 2t minus 3.
Okay, well, we'll see. I'm going to plug z equals t and x equals -1 or +1 minus 4t into equation 1. I could also choose equation 2. I do not want to choose equation 3 because we're going to check this in the third equation after we have it. So I'm plugging this in here so that I can find y. So I think here we get -2t, and then when we bring it over, we'll get +2t. And then I have 1 bringing over here, we get -3. Is that what you got as well, Aiden? Or did you get
Minus
something
3,
different?
yeah.
Okay, so, and you plugged it into equation 2.
Yes.
Okay, so we end up getting the same thing. Perfect.
Will that always happen?
I mean, it is the same line of intersection. So if we think about, like, we should get that last point the same, right?
Yeah.
For the direction vector and position vector.
What if it was a factor of that? What if it was -6 plus 4t? Could you reduce it?
No. Because that changes the position,
Oh,
the
yeah.
point vector.
I guess it wouldn't be the same.
Yeah. Okay, so we're going to sub the parametric equations above into the last equation. So let's say into equation 3 that we haven't used yet, which was our x plus 2y equals -5. This is nice and easy for us because we don't have to worry about, well, I guess z is just t anyways, but whatever.
You still have to collect like terms.
Yeah.
Well, I guess you do, but one has to.
Yeah. Okay, and then no fractions this time, which is nice. Okay, so we're noticing the t's will cancel. This happens anytime you have 0 points of intersection or infinite. Anil, really? This happens anytime you have 0 or infinite. And then the rest of what I want to check is if the constants, when I gather those together, does it give me a true statement? So either you will get what we had last question, where you get an untrue statement, like -39 equals 3. We know that's not true. Or you will get a true statement, which means that they have infinite points of intersection. So it's either 0 or infinite in these cases. And we actually know the line of intersection. What's the line of intersection?
-1, 3, 0 plus t, -4, 2, 1.
Okay, so I'm going to use my parametric equations to find the vector equation of the line of intersection above. So if you just take a look here, I have my position vector. Here it's 1, -3, and this one doesn't have a point up here, so 1, -3, 0 is my position vector. And my direction vector will be the scalar multiple of the t's, so it will be -4, 2, and 1. And that's actually my line of intersection. So I may ask you about that. If you have a particular line of intersection, tell me what that line of intersection is. So essentially, this is actually very similar to what we did yesterday in the sense that either I can get, when I do this same process for the same set of 3 planes, either I will get an always true statement like -5 equals -5, that tells me infinite. I can get an untrue statement like 10 equals 0, that tells me 0. Or if I can actually solve for a parameter here, like this, when we solve for t equals -3, that actually gives me the t that will tell me what the point of intersection is. So that is kind of what happens. So when you have infinite or 0 points of intersection, your t's actually always end up canceling out. So yeah. So same process. Use elimination with 2, find the parametric equations, and then sub it into the last one and see what happens with it. Okay? So once you've practiced these a little bit, you'll get the hang of the process. Okay, and then we're always going to make sure we check for parallel planes as well, because if we have parallel planes, we don't want to spend all of our time doing this. Save a lot of time by doing that. Okay? Questions? That was a long one, I know.